Sure. All right, it should be recording.
Okay. So my name is YZ. The fun fact about me is my full name is Yang Zhang, but I have been using YZ as my name for a couple of years. And it's because of Yang and Zhang, both are very common names in China. I was born in China and grew up in China. I came to US for graduate school. So, and I kind of like YZ for the simplicity, and be using that. I've been publishing paper with this YZ as my name since about maybe 2 years ago. Now I have a bunch of papers with this YZ as my name. So and now I'm thinking, actually not only thinking, I was able to convince my wife about changing her last name to be Z, and my kids too. And my kids are super excited. So, and those we're in the middle of changing our names, family names, officially to Z. Okay. So, without COVID, it might already happen, but everything got slowed down now. But at a certain time, you see even the website on our departmental website with my name should be changed to YZ. So you can just call me YZ now.
YZ, what's your wife's first name start with?
I can tell you my wife's last name. So that's another reason why it's confusing. My wife's last name was also Yang. It's the same as my first name. So that's very confusing. Anyway, so so coming back here, so Cover Lab to be Z Lab. So our research can be summarized in 3 words: molecules, materials, and machines. So the reason is our vision is, first we want to understand the emergent laws of nature from the molecular level. And then we create materials with desired properties. And ultimately, we want to build intelligent machines out of those the materials with the tailored properties. So this approach is fundamental science driven, yet it entertains a clear engineering goal, which is to make a positive impact to our lives. So, so on the fundamental science side, we work on 2 close related areas. And so one of them is the non-equilibrium physics and accelerated molecular simulation methods. So many of you, even you are freshmen, you may have learned a little bit of thermodynamics before. And one of the most intriguing laws of nature is thermodynamic laws, namely the second law of thermodynamics, the Boltzmann's second law of thermodynamics. It tells us that everything will evolve towards thermodynamic equilibrium, right? So that is the foundations of thermodynamics. So, but unfortunately, Boltzmann didn't tell us how long this process takes. It says that if wait long enough, then we have the theories that we can use to describe the collective behavior of materials. In reality, the thermodynamic equilibrium actually never gets there. If you look at the world around us, most of the systems are far from equilibrium. So, and this process to reach equilibrium is very, very long. So in our group, we strive to understand this phenomena and derive theories to describe this a wide range of long time scale phenomena. To give you one example, so like as nuclear students, we build nuclear reactors, and even as a non-nuclear students, as human beings, we build like airplanes, we build bridges, buildings. But we cannot predict how long they can last. Like many of our predictions and estimations of the life of nuclear reactors are very conservative. That's because we don't have a way to predict the long-term materials behavior and performance. So, and with the so-called first principles, like we teach in 446, 447, like quantum mechanics, we can only nowadays simulate like hundreds of thousands of items up to picosecond or nanosecond time scale. But what we really care in reality are like the materials aging and degradations over years time scale. So there's a huge gap, and that is the gap we're trying to fill in our group. So getting into the details, like we develop new computation techniques and making use of both physics and a lot of math. Nowadays, we use a computational topology. And this is also part of now the data science approach. This is the field called topological data analysis, TDA. So the idea is to understand the global shape of data, understand the topology of shape of data. And so this is one direction. The other approach is more like traditional physics approach. We do non-equilibrium statistical mechanics. So we develop those computation tools and for us to be able to predict the long-term behavior of materials. So like a model example is the flow of glasses, like our window glass. They are all flowing over millions of years. But nowadays, we don't have the power to predict this highly viscous liquid. And in our group now, with our method, we finally were able to solve this problem. So we also develop a lot of theories, kinetic theories. So this is there's a close link between the theories we develop and neutron transport for plasma students and also for like dense plasmas as well. And we also do experiments. Okay, so some of you may not know. So by training, I'm an experimentalist. So the experiments we do are not on campus. That's the reason you don't know we do all the experiments. Because the experiments we do, in order to see like how atoms move, we have to build big accelerators. Use X-rays and actually we use neutrons to not only see what the atoms are, but also see how they move. So we can take movies of the motions of atoms and molecules. And to do that, we have to use this facility. It's called Spallation Neutron Source at Oak Ridge National Lab. So I was there for 2 years before coming to Illinois. So I got my PhD in 2010. And then I was there from 2010 to 2012. So this to generate neutrons, and you know that we can use reactors, we can use nuclear reactors, but the other way to generate neutrons, we can use the spallation process. So you send high energy protons to high Z material like tungsten or mercury. And then for every spallation process, we generate like 20-ish neutrons, and then we can slow them down and use them just like light to see inside materials. So this is a very expensive technique. And in fact, it's probably the ultimate material characterization techniques we have. So for this so-called first spallation neutron source, and started from 2000, I think 2002 something, I think about 2002, maybe 2001. So, and took 7 years to build, and the cost was like 1.4 billion. And that alone is may not be impressive. Even after that, after 7 years, so the operational budget is like $250 million a year. If you divide a work day, it's like 1 million every day. So when we do experiments over there, and I always tell my students, each of our experiment will cost more than $1 million. It's literally more than $1 million. And today and tomorrow, actually, I am virtually at Oak Ridge to attend the review committee. And now we are very close to get the approval from DOE to build a second target station. See, you can see this. Okay, you can see my mouse, or we can see my mouse. There's an empty space here. So this is reserved for the second target station. And now everything's in place, and there'll be this is going to be another $2 billion project, which is going to be built in the next 10 to 20 years also. So we do closely compare our simulations with the experiments. Okay. So that's the method part. And for the system we study, okay, all kind of liquid systems. So from water to metallic liquids. So that include multi-component metallic liquids, which can form disordered metals like so-called metallic acid, and also some of the liquid metals which are used for many of the nuclear applications. Right? So, and we also work on ionic liquids, concentrated electrolyte solutions for flow battery applications. So for this project, we're funded by the Energy Innovation Hub from DOE. So it is the single largest project of DOE. Had 125 million for the first 5 years. It just got renewed for another 5 years, another 125 million, so total of $250 million. So the goal is to develop large-scale energy storage solutions, not only for like your cell phones or laptops. This is to store the energies we don't use at night or during the day. So even for nuclear reactors, we keep generating the electricity continuously when we don't use them. So nowadays, all of them are just dumped on the power grid. So we need this important energy storage to be part of the overall energy storage solution. And lastly, we work on molten salts. Right? There has been a lot of excitement about the molten salt reactors. But the fundamental properties of molten salt is still not well understood. So here we do a lot of administrative skill computation to understand, for example, the viscosity, the solubility of the fuels inside the molten salts. So those are just a few different liquid systems we study. So related to what you may know, so if you are a junior, senior, maybe you already learned fluid mechanics. So in that sense, our work is centered around the molecular fluid mechanics. We want to understand the fluid mechanics from the atomic molecular level. So, and we also work on a bunch of other materials, and they are pretty fun things to work on, like some self-heating materials, which can grow together after mechanical damage. We work on biomaterials, proteins, to prevent the denaturation of proteins by putting them in nanopores. And so we'll work on this molecular cage, which can be used to store gas for like gas extractions or catalysis. So like most of these porous materials, they have huge surface area, and most of them are solid, but now we can make them into liquid. Then you can run them through cracks, right, for extraction, for cleaning. So there are a bunch of real system we work on. Okay, so this is half of my research group. So the other half seems very different, but there's a very close link between these two areas. The second part is really on robotics, machines. So in this area, we work on so-called soft robotics. So soft robotics, they are made of soft materials like polymers, gels. So they're intrinsically safe. So we use a bio-inspired principles to design like a flow regulator to control the airflow, fluid flow. And then we build a 3D printer, those microchannels, and build this soft robotic arm. So I can spend a lot more time on that, but I think I probably wouldn't do that today. So, but anyway, so this is a second project. It's more hands-on. We have a lab in Talbot, and we have some undergraduate students working in this area as well. So the first part usually requires maybe some more background in terms of physics and math and computations. So undergrad students are also welcome to join, and I do have undergrads attending our group meetings. But just the barrier to getting started is slightly higher. And the second part is it's very hands-on, and we have a lot of fun projects. We even we have outreach activities during the summer, bring in like high school students and to work on the soft robotics. And sometimes we also have tours from elementary school students. So anyway, so those are the two areas and we work on. So the connection is really computing, so intelligent computing. So we do lots of machine learnings nowadays. Well, I don't really like the terminology machine learning, so I've been using them all the time. Just didn't call them machine learning until like in the last couple of years. So like for instance, so here the first area we use it's called TDA. So this is really beyond the machine learning method that is widely used now. This is the next level of data science methods called TDA. So compared to the machine learning that you know, the machine learning is like black box. It doesn't provide you much intuitions. So this TDA method is supposed to be able to provide more insights on what is going on in the data sets. This is the ongoing research called like understandable AI or explainable AI, XAI, explainable AI. So the computers understand that's good. We also want to understand by ourselves. Okay. And in our molten salt project, we developed so-called neural network force field, okay, to without getting into details of interactions, and we still want to accelerate the simulations. And in this soft robotic arm system, we use a deep reinforcement learning to control how they move. Actually pretty fun to train the motions of soft robotic arm. So anyway, so that is a summary of our research. And so next slide, I want to show you. Okay, so we want to have you as many other students as possible in our group. And we have multiple openings. So how do we join us? How to join us? So first, I need you to have a very good coding skills. So in both our projects, we use lots of codings. So just to give you a sense, many of you may know Python and know how to use Python. So the first thing I tell my students is Python is for the amateurs. Okay? So if you want to get into the real computation, you have to learn some of the compiled languages, okay, like C and C++. So, and of course, you have to make use of a lot of the modern computer science tools. So the second is, I guess, kind of a skill I'd like you to have is some solid trainings in physical science and GPAs. So that can be reflected by your GPA, right? So if you're nuclear students and you get trainings of different kind of physical science engineering. Okay. And if you're interested to join our group, please send me the 3 things. So number 1 is your CV. So if you have any research background, so I know for freshmen, you may not have many things to put there, but that's fine. So if you have any experience relevant to the project is helpful. So 1, the CV, and 2nd is visual translate what course learn, and maybe recommend some courses you may need to take in order to join our group. And number 3 is some code samples. I want to see like your coding skills. Okay, it doesn't have to be enough for me to tell about your coding skills. If you want, you are still in a variable and code. So this is my email and our group website. Some information there. So now in our group, I have I think each graduate students and postdocs. So some students are graduating, some joining us. Usually like 10-ish graduate students and graduate students and postdocs. So that is all about my own. But I have 2 more things I added here that I want to mention to you. So it's very, very new. Okay, so this is part of my duties, the associate head for graduate program at NPRE, and I pushed forward a new, I guess, a new thing for our own undergraduate student. So the motivation is to encourage more and more of our undergraduate students here at graduate school. And so to help with that, those that you can provide
Sorry, Professor, you're breaking up a little bit.
Okay.
Professor, you might need to.
How about now?
That's good so far.
Really finalize the final wording. That's why you haven't seen those yet. But basically, if you have an undergrad degree from NPRE and if your GPA is above certain threshold, then we're going to minimize the effort for you to get into our graduate program. Okay, so you don't have to go through the regular applications waiting to I don't know, like deadline for the fall admission deadline January, and wait for the decisions like April 15th, and submit recommendation letters and all of those. Okay, so we hope to make this process much simpler and much sooner, so that we can tell you, like, for example, like now it's September, October. So before the end of this year, we can tell you maybe you will be admitted to our program 99.99% of the chance. Okay, so you don't have to worry about other things. So just stay tuned. This comes officially very soon. So I don't want to give you the exact number of GPA will occur and the details. Just want to let you know something's coming up for our undergraduate students to make it much easier for you to stay here for graduate school. And the second one is it's related to our robotics project, and the talk already recorded my talk. So this on an event called Illinois Ignite 2020. So this is event organized by jointly by our Office of Technology Management and U Chicago, Northwestern, and Illinois state government. So they invite a lot of government officials and venture capitalists. I think
Sorry, we lost you again, Professor.
It's free, register. Okay, sorry about that. So I'm going to post a link to this event. So I'm going to post the link to this event, and it's free. So if you're more interested in our robotics project, I have a presentation over there. Oh, it's more time than expected. Let me just stop sharing. So Nathan, do you mind stop recording? And I can take a few